In this video, we're going to go over Deutsch's algorithm, which is a simple quantum algorithm to obtain some information about a specific function f of x, where f of x acts on a single bit and returns a single bit. So, in fact, there's only 4 possibilities for what f of x could actually do, because we define it on its action on the input, which is 0 and 1. So we have 4 possibilities. We have f1, where f0 is equal to 0, and f1 is also equal to 0. So that's one possibility for f of x. And then we could think of another function. Perhaps f of 0 is equal to 0, but f of 1 is equal to 1. Or we could have the reverse. f of 0 is equal to 1, and f of 1 is equal to 0. And then finally, the last possibility is that it's f of 0 is equal to 1, and f of 1 is also equal to 1. So Deutsch's problem and Deutsch's algorithm essentially deals with this simple f of x function, but separates these 4 functions into 2 different types. So we can call f1 and f4 constant, which means they return the same value for all their inputs. And that's clear. f1 just returns 0, f4 returns 1. And then f2 and f3 can be grouped into what we'll call balanced. And balanced just means there's as many zeros as there is ones in the function output. So Deutsch's problem asks, given access to some unitary, some oracle that's going to implement f of x for us in the standard way, where we have our input and output register, and applying u of f is going to give us this state right here. Deutsch's algorithm asks, how many times do we need to execute u of f to determine whether it's constant or balanced? So this is a really good example to see the power of quantum computing, because it's clear that any classical algorithm, given access to this function f of x, requires at least 2 iterations, because you have to execute f of x on 0 and also 1 if you want to know whether they return the same value or not. That's clear. But it turns out with a quantum computer, if you have access to a quantum computer, all you need is 1 call of this u of f. So let's take a look at how that works. Let's prepare the following state. We're going to prepare 0 in the input register. So I'll call this in, and then 1 in the output register. So this is step 1 in Deutsch's algorithm. Now, step 2, let's put a Hadamard on both of these states. So Hadamard tensor Hadamard on our input and output. And of course, this is going to give us 0 plus 1 over the square root of 2, and then 0 minus 1 over the square root of 2. Now, before I move on to step 3, which is going to be applying this u of f on our state, I want to examine what happens in the more general case where we don't actually make any assumptions about the input register, but we know that the output register is in this superposition, because the fact that we have this particular state with this minus sign here is going to do something kind of interesting after we apply u of f. So let's see what happens. Let's apply u of f right now. And we can follow the rules of linear transformations to find that the state we get here is f of x minus the negation of f of x. because f of x XORed with 0 is f of x. F of x XORed with 1 is the negation of f of x. Now let's say f of x is equal to 1 for our particular input. Then our resulting state, or let's say, in fact, it's 0. What is our resulting state going to be? We plug in f of x, we have 0 here. We plug in the negation of f of x, and we have 1. So nothing happens to this state. Let's say instead f of x was equal to 1. Then we have our input register, and instead of 0, we put 1 here, and instead of 1, we put 0, right? So you kind of get this flip, but given that we have this minus sign here, this is actually just the original state times minus 1. And this gives us a nicer way of representing our state without actually having to talk about these different values, because we can just say u of f on the input, and then our output register in this state is just equal to negative 1 to the power of f of x times the state that we had. So what we've done is we've changed a bit flip that would have happened by applying u of f onto the output register. We changed the bit flip to an overall change of sign. So now we have this phase factor, this sign flip that's going to depend on the value of f of x. So now we can return to what's going to be step 3 now, where we apply u of f to our state. And remember, now our input register is in this superposition. And we want to use the example that we just illustrated to see what we get when we apply u of f here. And let's make things a bit easier on ourselves and just start referring to this second qubit state as the minus state. And so now we have this equivalence between 0 minus 1 over the square root of 2, and we're just calling it this minus state. So just to be clear, u of f on the input times the minus state is negative 1 f of x input times the minus state. Okay, so now we can return to our state here before applying u of f. And let me rewrite it. We have this normalization outside here. And we have 0 times the minus state plus 1 times the minus state. So what happens when we apply u of f onto the state? Well, we can just refer to what we figured out when we went over that example. And what we're going to get is this state over here, negative 1 to the power of f of 0 times the minus state plus negative 1 f of 1. Oh, I forgot the first qubit. 0, and then the minus state. And then we have 1, and then the minus state here. So let's just pull out our minus state now, just to make things more clear. And we have negative 1 to the power of f of 0 times 0 plus negative 1 f of 1 times 1, and then this minus state outside. So now we can just think about what are the different possible states here. Well, let's say f of 0 is equal to f of 1. So they could either both be 1 or they could both be 0. right? So if they're both 1, then this is just going to be a minus sign, but this is also going to be a minus sign. So there's going to be no like relative sign change between the two. There might be an overall minus sign, but we know that this will be a plus if we just pull out the minus. So we can say plus minus 0 plus 1 over the square root of 2 times this minus sign. If f0 is equal to f of 1. Now, let's say they're not equal. Then we can just, if they're not equal, then we know one of these is going to be positive, say this one, and then this is going to give us a negative, or it could be flipped. So we can, again, just pull out a minus sign, and we know that the difference between the two is they're going to have a different sign. So we have plus minus 0 minus 1 over the square root of 2 times our minus state. If f of 0 is not equal to f of 1. So now here comes the key part. Let's apply a Hadamard to the first state. What happens if we apply a Hadamard to this state, for example? Well, this is the result of Hadamard onto a 0, and the Hadamard gate is a unitary gate, so if we apply it again, we should go back to 0. Likewise, this state over here is the result of applying Hadamard to a qubit in the state 1, so if we apply it again, we'll go back to 1. So after applying a Hadamard to the state, our result is 0, and then minus over here. If f of 0 is equal to f of 1, but over here we have 1. And this is the case where f of 0 is not equal to f of 1. And let me rewrite this. We can rewrite this as the first qubit just ends up in the state f of 0 XORed with f of 1, and then a minus. And we actually don't really care about the output register anymore, because now, as you can see, we've kind of encoded our relevant information into the input register, which is kind of interesting. You'd expect that since f of x is being executed in some sense on the output register, we'd want to worry about the output register. But now we have this information about our function f of x. And notice that this right here is actually a global property of f of x. What does that mean? It means it encodes information not about a single local input, but the entire range of inputs. And that is the key thing right there. There's nothing classically that we can do with one execution of a function to determine any sort of global property of that function. We only get little glimpses of local information when we're working on a classical computer. Clearly, that's not the case on our quantum computer. So now let's say we measure our input register. Well, we're going to get 0 if f of 0 is equal to f of 1, or f of x is constant. And we get 1 in the other case, where f of 0 is not equal to f of 1. And in this case, f of x is balanced. And this is the solution to Deutsch's problem. This is Deutsch's algorithm right here. Just like that, as you can see, it only required one execution of u of f. And of course, classically, we would require 2. So, and this isn't like the most practical speed up, but it's a very important and illustrative example to see the difference in how quantum information is handled rather than classical information. And it has to do with this fact that we're sort of obtaining this interference between different states and different function outputs. That's something entirely not classical. And in the following videos, we'll see how we can extend this idea to more practical tasks and more interesting algorithms. So, thank you.